In this podcast, we're going to talk about the integrated rate law, but first I thought we'd do a little bit of kinetics review. Remind you that we've been working with the differential rate law so far. We are given concentration of a reactant versus rate data, and then we compare the value of the concentration, see how it changed, and see how the rate changed to determine the order. Now we're going to be working with the integrated rate law. Integrated rate law gives us concentration versus time data, and we're going to need to make 3 graphs in order to determine the order of a reaction. Alright, so with the integrated rate law, as I said, we'll have to make 3 different graphs. The first graph is going to be a concentration versus time. The second one is a natural log of the concentration versus time. And the third one is the 1 over concentration versus time. Now, whichever of these graphs gives us the most linear graph, or the line that is the most linear, is going to tell us the order of that reaction. So if it's a linear line at concentration versus time, then it's 0 order. If it gives us a linear line at the natural log of concentration versus time, it's first order. And if it gives us a linear line on the 1 over concentration versus time graph, then that is second order. Just remember that rate is we're always talking about the disappearance of reactants over time. They're turning into products. So we're going to have a negative change in the concentration of the reactants, and then that will be divided by the change in time. That's going to give us our rate. All right, so first we're given a little data. You should have this in your guided notes. And we need to graph this data. So first graph we need to make is concentration versus time. So this is what our first graph should look like. We're going to go and we're going to run this data in our rate laws program. And we should come back with some values. All right, so first we see that we have the linear regression analysis, and the value we want to be concerned with is r squared. R squared tells us how close to a linear line is the line that we actually have. The closer it is to 1, the better the more linear that line is. So this r squared value is going to be 0.9687, so close to linear but not quite. So we're going to need to keep graphing to try to get a better value. All right, so now the next thing we want to graph is the natural log of the concentration versus time. So this one looks pretty linear just from looking at it. And then once we run our regression analysis, we see that the r squared value is 0.99979. So that's pretty close, probably as close as we'll get to having a value of 1. So this tells us that the natural log of the concentration versus time is the most linear for that data, which means this is a first order reaction with respect to N2O5. Alright, and now that we know that it's first order because of that r squared value, we also know the equation of that line. So this is the integrated rate law, or the equation of the first order graph. It's the natural log of the concentration equals negative kT plus the natural log of the original concentration. We already know that a natural log of the concentration versus time is where we get a straight line. And the slope is going to be negative k. So up here in this form, it is y equals mx plus b form, with the negative k being our slope. So if we wanted to find our slope of this line, we just need to look at our regression analysis. So here we see in our regression analysis that a is negative 5.98 times 10 to the negative 4th. We also know that the slope is negative k. So if we take the positive of this, that'll be our k. So our k is 5.98 times 10 to the negative 4th for the natural log versus time graph. All right, let's look at a different problem. All right, this next problem, we're going to graph a different set of data. We're going to start out with the concentration versus time graph. I think it looks very linear, but when you run a regression analysis, you see that the r squared value is only 0.927. So that's really not very linear. So it's not a 0 order reaction. So we need to keep going. All right, now we graph the natural log of the concentration versus time. And again, looks linear, but when you run the regression analysis, you see that it's actually close to linear, but not quite. So our r squared is 0.9824 this time. Let's go ahead and take it one step further into the 1 over concentration versus time graph to see if we can get an r squared value that's more close to 1. All right, 1 over concentration. And when we run our regression, we see that it's 0.99997. So this would be the best graph. Because it's 1 over concentration versus time is the most linear, that means this is a second order graph. Now because it's second order, we can write the equation of the line, which is 1 over the concentration equals kT plus 1 over the original concentration. We know that the 1 over concentration versus time graph is what produces the straight line. And again, because this is in y equals mx plus b form, the slope is k. But for this one, it's positive k, not negative k. So if we look at our regression analysis, again, looking at the letter A, because that's where the k would be, we see that our k for this equation is 0.543. All right, you can also calculate slope by hand by looking at your data. So you can just do the change in y, which is the 1 over concentration for that last graph, over the change in x, which is time. So change is y goes from 263.2 to 100, so the change is 163.2. And then we know that the slope, or the x, would go from 300 to 0. So that's 300, a change of 300. So our slope is 0.544, which is pretty close to what we got with our regression analysis. Now, you remember that from that very first little slide, the change is always negative. So this is negative. Okay, and then when you plug that in down here, it takes away the negative, and you end back up with a positive slope. Okay? All right, again, if you, the much easier way to do this, if you have a graphing calculator, is just to look at your regression results, read the A, because that will always be your K. All right, the last rate law that we need to talk about is zero order. Zero order rate law, the concentration doesn't even matter. So the rate does not change with concentration, so the rate really is just K. It's dependent all on K, the rate constant. Here's the equation that describes a zero order graph. It's the concentration of A equals negative KT plus the original concentration of A. You get a straight line from the concentration versus time graph. And again, your slope is going to be negative k. So for zero order and first order, the slope is negative k. And for second order, the slope is just plain k. Zero order rate laws usually occur when you have a reaction that occurs on a surface. That's because the surface area stays constant. So after the surface is all taken, it doesn't matter how much more reactant you put in, only the amount that the surface can hold will actually react at one given time. Enzyme chemistry is another great example of zero order reactions because there's only so many enzymes that can be active sites. So once they're all filled up, there's really nothing else you can do. This last slide is just a summary slide that shows all of the things that we've talked about so far for zero, first, and second order. So I'm going to close out with this slide so that you can remember what all we've done and what all you've learned.